In question 1, for the particle A with a mass of 4 kilograms and the particle B with a mass of 2 kilograms, they are moving towards each other in opposite directions. They collide directly. Before the collision, A is moving with a speed of 2u and B with a speed of 3u, and immediately after the collision, the speed of B is 2u meters per second. We are additionally told that the direction of motion of B is reversed by the collision, and we need to find, in terms of u, the speed of A immediately after the collision. So I will start by drawing the two particles A and B with masses of 4 and 2 kilograms respectively. Originally they are moving towards each other, so 2u and 3u are the speeds respectively. And then we are told that immediately after the collision, B is moving with a speed of 2u meters per second and it's moving to the right. And I will assume that A is also moving to the right with a speed of v. So this is the situation. I will be using the conservation of linear momentum, where it says that the momentum before is equal to the momentum after the collision. So we've got 4 times 2u plus 2 times negative 3u, because the particle B is moving to the left, so the speed is 3u, but the velocity is negative 3u, is equal to 4v plus 2 times 2u. So this leads to 8u minus 6u is equal to 4v plus 4u. So we got that minus 2u is equal to 4v, and therefore v is minus u over 2. Now the speed is the magnitude of the velocity, so we have to say that the speed is equal to u over 2 meters per second. The negative sign indicates that v is not to the right, it's actually to the left. And therefore, when we are asked to state the direction of motion of A immediately after the collision, we simply need to say that it's going to be opposite the original direction of motion. In part C, we need to find, in terms of u, the magnitude of the impulse received by B in the collision, and we need to state the units of our answer. Well, we know that the impulse is the change in momentum, so we are considering the particle B here. So the momentum after the impact is going to be 2 times 2u, and the momentum before the impact is 2 times negative 3u. This gives an answer of 4u plus 6u, so it's 10u, and the units are Newton seconds, or alternatively, you can give kilograms meters per second. In question 2, a particle P rests in equilibrium. We've got a system of 3 forces, F1, F2, and F3 applied to P, and P remains in equilibrium, and we need to find F3 in terms of C, I, and J. Well, we know that the sum of the forces, the resultant, is going to be 0 because P is in equilibrium. So we've got F1 plus F2 plus F3 being equal to the 0 vector, which means that F3 is equal to minus F1 minus F2. We know that F1 is 3Ci plus 4Cj, whereas F2 is negative 14I plus 7J. I will be collecting everything together. The I component is going to be minus 3C plus 14, whereas the J component is going to be minus 4C minus 7. So overall, this is the expression for F3 in terms of C, I, and J. The force F3 is removed from the system, C is 2, and we need to find the size of the angle between the direction of the I vector and the direction of the resultant force acting on P. So the first thing to do is use the fact that C is 2 to find the force 1, so F1, it's going to be 3 times 2 the I component and 4 times 2 the J component. This gives me 6, 8. This is the F1, and the resultant is simply the sum of F1 and F2. This is because the F3 has been removed, so I'm going to be doing F1 plus F2, which is equal to 6, 8. This is F1 plus negative 14, 7. This is F2, which gives an answer of negative 8, 15. So I can proceed by drawing the force. There it is. It's going to the left and up. The vector I is the vector pointing to the right. We're trying to find the angle between these two directions. I will call it a theta. So it makes sense to find the acute angle here, which I will call phi, and then proceed by doing 180 minus phi. So let's start with tan phi, which is equal to 15 over 8. This makes phi to be 61.9275 ... and therefore theta is 180 minus the 61.9275 ... which gives an answer of 118 degrees. This is the angle between the resultant, the F1 plus F2, and the vector I. We then have that the mass of P is m kilograms and the magnitude of the acceleration of P is 8.5 meters per square second. We need to find the value of m. I will start by stating that the force is equal to mass times the acceleration, and I will be taking the magnitudes of these because I'm told the magnitude of the acceleration, so I will be working with the magnitude of the force, the magnitude of the acceleration, and the magnitude of m, the mass. It's simply the value itself of the mass. So we have found that the force is negative 815, so I will take the magnitude of this is equal to 8.5, which is the magnitude of the acceleration times m. So to find the magnitude of negative 815, I will simply be doing minus 8 squared plus 15 squared and all square root being equal to 8.5 m. This leads to 17 being 8.5 m, and therefore m is equal to 2. In question 3, two students observe a book of mass 0.2 kilograms falling vertically from rest from a shelf that is 1.5 meters above floor. Student A is suggesting that we model this as a particle falling freely under gravity, and we need to use this model to find the time taken for the book to reach the floor. So we've got the book initially at rest, so u is 0 meters per second. We've got a distance, a displacement of 1.5 meters, and we know that the acceleration is g, which is 9.8 meters per square second. So I'll be using s is ut plus a half at squared, leading to 1.5 is 0 plus a half times the 9.8 times t squared. So we're looking at 1.5 is 4.9 t squared, leading to 15 over 49 being t squared. I will take the square root of 15 over 49. We will plug this on the calculator, giving an answer correct to 3 significant figure, which works out to be 0.553 seconds. If you give more accuracy or you give an exact answer, you will be penalized because we've used g to be 9.8. Anything to 2SF or 3SF would score all 3 marks. We then have student B, who is suggesting an improved model where the book is modeled as a particle experiencing a resistive force of magnitude r newtons. The time taken to reach the floor is now 0.6 seconds, and we need to use this model to find the value of r. Well, I will start again with s is ut plus a half at squared. The distance covered is still 1.5. The initial speed is 0, and we've got a half times a times the 0.6 squared. This leads to 1.5 is equal to 0.18a, and if we divide both sides by 0.18, we get 25 over 3 to be the acceleration that the particle is experiencing. So it makes sense to draw a quick sketch. We've got the particle is feeling its weight of 0.2 g pointing downwards, and we've got this resistive force of magnitude r pointing upwards. The overall motion is downwards, so we've got acceleration of 25 over 3 downwards, and therefore we can say that the forces acting downwards, 0.2 g, minus the forces acting upwards, which is r, is equal to mass times acceleration. So we need to solve for r. We get 0.2 times 9.8 minus the 0.2 times 25 over 3 is equal to r, and this gives a value of r of 0.293. Again, we need to give our final answer in 2SF or 3SF. More accuracy will be penalized. In question 4, we've got the beam AB having a mass of m kilograms, a length of 2 meters. It's suspended by 2 light vertical ropes at C and D. The beam is in equilibrium in a horizontal position. We are attaching a particle of mass pm kilograms at point A, and the beam remains in equilibrium in a horizontal position. The beam is modeled as a uniform rod. and we need to use the fact that the tension in the robot C is 4 times the tension in the robot D to find the exact value of P. So I will start by adding all the forces on my diagram and all the distances. So we've got the mass of PMG at A. This is the particle that was attached at A. We've got the weight of mg at the middle because we are assuming we are modeling the beam as being a uniform rod, which means that the center of mass is at the midpoint. And we've got tension at C and tension at D. I'm planning on taking moments about A. So the distance of C from A is 0.6. The distance of the center of mass mg from A is 1 meter. And the distance of D from A is 1.8 meters. I simply did 2 meters minus 0.2 meters. So we've got that the forces acting upwards, which are TC plus TD, is equal to the forces acting downwards, which is PMG plus MG. And in addition, we've got that the tension at C is 4 times the tension at D. So if we take moments about A, we've got the clockwise moment because of the weight at the distance of 1 meter. So we've got 1 times mg being equal to the anti-clockwise moment because of TC. So this is acting at a distance of 0.6 meters. So it's 0.6 TC plus 1.8 TD. So I will proceed by replacing TC with 4 TD, leading to mg is equal to 0.6 times 4 TD plus 1.8 TD. So we've got that mg is equal to 2.4 TD plus 1.8 TD, and therefore we have that mg is 4.2 TD. Well, I will divide both sides by 4.2, leading to 5 mg over 21 is equal to TD. So I will proceed in finding TC. So TC is equal to 4 times TD, which is 5 mg over 21, which means that TC is equal to 20 mg over 21. So I've got both the tension at C and the tension at D. I will be substituting into this equation here, and I will be solving for P. So TC, which was found to be 20 mg over 21, plus TD, which is 5 mg over 21, is equal to P mg plus mg. I will divide throughout by the mg, so the mg's cancel out, and I've got on the left hand side 25 over 21 is equal to P plus 1, and therefore P is equal to 4 over 21. Remember that you are asked to find the exact value of P, so if you proceed in giving this to 2 or 3SF, you will be penalized. We then have that the particle of mass Pm kilograms at A is removed and replaced by a particle of mass Qm kilograms at A. The beam remains in equilibrium in a horizontal position, but is now on the point of tilting, and we need to use this model to find the exact value of Q. So once again, let's look at what's happening here. We have replaced the particle at A with a particle of mass Qm, and we are on the point of tilting, so we are about to tilt about C. This means that there will be no tension at D. So this time we've got that the forces acting upwards, which is TC, is equal to the forces acting downwards, which is QMG plus MG. And I will proceed once more by taking moments about A. We are looking at 1 times mg, which is the clockwise moment, is equal to 0.6 times TC. So we've got that mg is 0.6, and TC will be replaced with QMG plus mg. I will be expanding this to get mg is 0.6 qmg plus 0.6 mg. Obviously, I will be cancelling out the mg's, leading to 1 is equal to 0.6 q plus 0.6. So 0.4 is equal to 0.6 q. Therefore, q is equal to 2 over 3. Once more, we've been asked to find the exact value of Q, so I will give it as a fraction. If I proceed in giving answers to 2 or 3 SF, I will be penalized. Finally, we're asked to state how we have used the modeling assumption that the beam is uniform. We already discussed this. We said that the weight of the beam is acting at the middle. In question 5, we've got the speed-time graph in figure 2 illustrating the motion of a car traveling along a road. At time t0, it starts from rest, as we can see, accelerating uniformly for 30 seconds, attaining a speed of v, and maintaining this speed until t is capital T. We need to show that the distance traveled by the car between t0 and t is capital T is given by capital V times capital T minus 15. Well, we know that in a speed time graph, the area under the speed time graph gives me the distance. So in this case, we're looking at the trapezium. Base 1 is capital T, base 2 is capital T minus 30, and the height of the trapezium is capital V. So this is going to be capital T plus capital T minus 30, and all of it divided by 2 times capital V. So we're looking at 2t minus 30 over 2 times capital V, which is of course V times t minus 15 as required. We are then told that the motorbike is also traveling along the same road. It starts from rest at time t is 10, accelerating uniformly for 40 seconds. The acceleration of the motorbike is the same as the acceleration of the car. It then travels at a constant speed for a further 10 seconds and then decelerates, reaching a speed of capital V at time capital T seconds. And we need to sketch the speed time graph for the motion of the motorbike. So the motorbike sets off at T is 10. The two lines here are parallel because both are having the same acceleration. We then maintain a constant speed, so we were accelerating for 40 seconds, so this here is 50, and then we've got a constant speed for 10 seconds, and then we decelerate uniformly, reaching a speed of capital V at time is capital T. We're then asked to show that the constant speed of the motorbike is 4 capital V over 3, so I will call this speed here to be V underscore M, and I will be using the fact that these two lines here have the same gradient, they are parallel, so the gradient of this line is given by capital V over 30, and this is equal to the gradient of the other line, which is capital V underscore M over 40, because the run here is 40 from 10 up to 50. I will cross multiply to get 40 V over 30 is equal to V underscore M. The zeros will cancel out, and we'll get that 4V over 3 is equal to V over M as required. We're then told that at time t is capital T seconds, the distance traveled by each vehicle is the same, and we need to find the value of capital T. We already know that the distance covered by the car is the area here, which is given by V times capital T minus 15. So the distance covered by the motorbike is the area shaded here, which consists of a triangle, a rectangle, and a trapezium. So I will be equating the two distances. So for the car, we already have V times T minus 15, which is equal to the area of the triangle, which has a base of 40 times Vm, where we have found Vm to be equal to 4V over 3. So we are looking at 40 times 4V over 3 over 2, that's base times height over 2, plus for the rectangle, which is a base of 10 times the height of 4V over 3. So we're looking at 10 times 4V over 3, plus the trapezium, which has a base 1 of 4V over 3, a base 2 of capital V, and a height of T minus 60. So we're looking at 4V over 3 plus the V over 2, that's base 1 plus base 2 over 2, times the height of capital T minus 60. So we're looking at capital V times T minus 15 being equal to 80 capital V over 3 plus 40 capital V over 3 plus 7V over 6 times T minus 60. So we observe that V is a common factor, so I will cancel it out, and we've got that T minus 15 is equal to 40 plus 7T over 6 minus 70. I will multiply throughout by 6 to get that 6T minus 90 is equal to 240 plus 70 minus 420. I will be collecting the numbers on the left-hand side, so we're looking at minus 90 minus 240 plus 420 is equal to 70 minus 6t, which leads to t being equal to 90. In question 6, we've got a particle of weight W newtons lying at rest on a rough horizontal surface. A force of magnitude P newtons is applied to the particle. We are given that tan alpha is 4/3, the coefficient of friction mu is 1/4, and given that the particle does not move, we need to show that P is less than or equal to 5W/8. The first thing to do is obviously to add all the forces on the diagram. We've got the weight, which is capital W, and obviously there's a reaction here. I will then be resolving the P here. We've got a horizontal component of P cos alpha and the vertical component of P sine alpha. And of course the force of P cos alpha is acting to the right, and therefore we must be having friction acting to the left. We also know that tan alpha is 4/3, so I'll be drawing a right angle triangle here. We've got opposite over adjacent. It's a 3, 4, 5 triangle, and therefore sine alpha is 4/5 and cos alpha is 3/5. I will proceed by stating that the forces acting upwards, which is R, is equal to the forces acting downwards, which is P sine alpha plus W. So this is the first equation. R is equal to P sine alpha plus W. And we also have forces to the right is equal to forces to the left. So P cos alpha is equal to F, and we know that the frictional force F is less than or equal to mu R, which is the maximum frictional force. So F is P cos alpha is less than or equal to mu, which is 1/4, times R, which is P sine of alpha plus W. I will cross multiply to get 4P cos alpha is less than or equal to P sine alpha plus W. I will be replacing cos alpha with 3/5, so 4P times 3/5 is less than or equal to P times sine alpha, which is 4/5 plus W, and I will be multiplying throughout by 5 to get 4P times 3 is less than or equal to 4P plus 5W. So we're looking at 12P less than or equal to 4P plus 5W, leading to 8P being less than or equal to 5W, and therefore P is less than or equal to 5W/8 as required. In question 7, we've got a car of mass 1200 kilograms towing a trailer of mass 600 kilograms. The road is inclined at an angle alpha, with sine alpha being 1/12. The driving force produced by the engine of the car is 3000 newtons. The car is moving with an acceleration of 0.75 meters per square second. We are additionally told that the non-gravitational resistance to motion of the car has a magnitude of 2R newtons, while for the trailer it's R newtons. We are modeling both as particles. We are modeling the tow bar as being a light rod parallel to the direction of motion, and we need to show that the value of R is 60. So we need to start by adding all the forces. We've got the weight of 1200 G. We've got the weight of the trailer, which is 600 G. We've got the driving force on the car of 3000 newtons. And then we've got the component of the weight plus the non-gravitational resistive forces acting on the car and the trailer. So we're looking at 1200 G sine alpha plus 2R on the car and 600 G sine alpha plus R on the trailer. And we've got an overall acceleration of 0.75 meters per square second. So I will be considering the car and the trailer together. So I'll be doing forces acting upwards minus forces acting downwards is equal to mass times acceleration. So we've got 3000 minus the 1200 G sine alpha plus 2R plus the 600 G sine alpha plus R is equal to 1200 plus 600, which is the combined mass, times the acceleration of 0.75. I will be replacing G with 9.8 and sine alpha with 1/12. So we're looking at 3000 minus 1200 times 9.8 times 1 over 12 minus 2r minus 600 times 9.8 times 1 over 12 minus r is equal to 1,350. This simplifies to 1,530 minus 3r is equal to 1,350, and therefore we're looking at 180 is equal to 3r, which means that r is equal to 60 as required. We're then asked to find the tension in the tow bar. So if we consider the trailer here, it's feeling a tension up the road. That's the tension in the tow bar, so that's capital T. And similarly, the car is feeling the same but opposite direction, so a capital T pointing downwards. Well, I will be focusing on what's acting on the trailer. So we consider the trailer, we've got forces acting upwards, which is capital T, minus forces acting downwards, which is 600 G sine alpha plus r is equal to mass of 600 times the acceleration of 0.75. So we're looking at T minus 600 times the 9.8 times the 1 over 12 minus r, which we found to be 60, so minus 60 is equal to 450, and therefore T minus 550 is equal to 450, which means that T is equal to 1,000 newtons. Now, when the car and the trailer are moving at a speed of 12 meters per second, the tow bar brakes. The non-gravitational resistance to motion remains unchanged, and we need to use the model to find the further distance moved by the trailer before first coming to rest. So first of all, the tension will go away because the tow bar brakes. We no longer have the acceleration of 0.75 meters per square second, so we will be considering the trailer. We've got no forces acting upwards, it's just the forces acting downwards of 600 G sine alpha plus r. So we're doing 0 minus the 600 G sine alpha plus r is equal to mass times acceleration. So we're trying to find the new acceleration. We know that it's actually decelerating, so we expect a negative result. So we're looking at minus 600 times the 9.8 times the 1 over 12 minus r, which we know is 60, is equal to 600a, and therefore we've got minus 550 is equal to 600a. So we get a value of a of minus 11 over 12. As expected, it's negative. I will then be using v squared is u squared plus 2as because the trailer is experiencing constant acceleration. We are interested in the distance before first coming to rest, so the final velocity will be 0. The initial is 12 squared, it was given to us, plus 2 times the acceleration of minus 11 over 12 times s. This leads to 0 is 144 minus 11s over 6. So we get 11s over 6 is equal to 144. Now if I divide 144 by 11 over 6, we get an answer for s, the distance covered, of 78.5 meters, correct to 3 significant figures. In question 8, we've got a square floor ABCD centered at O, modeled as a flat horizontal surface measuring 50 by 50 meters. We are told that all position vectors are given relative to O. We've got a small robot R programmed to travel across the floor at a constant velocity. Well, initially it's at negative 2i plus j. 11 seconds later it's at 9i plus 23j. And we need to find, in terms of t, I, and j, an expression for r, which is the position vector at time t seconds. Well, we know that since we are traveling with constant velocity, there is no acceleration. Acceleration is 0. So the position vector r is given by the initial position vector plus ut. U is the velocity. So we knew that when t is 11, we were at 9i plus 23j. So this is equal to minus 2i plus j, which is the initial position vector, plus 11u. This will help us determine the velocity vector. So if I collect all the i's and the j's on the left-hand side, I get 9 plus 2, it's 11i, plus 22j is 11u, and therefore the velocity vector is I plus 2j, so that's my u. so I can proceed. My general position vector is the initial position vector of minus 2i plus j plus t times the I plus 2j. I will be collecting the I components together, so this leads to R is minus 2 plus ti, and I will be collecting the j components together, leading to 1 plus 2t j, and all of this is meters. This is the position vector of the robot t seconds after starting motion. We're then told that the second robot S is at the point C. At t0, S leaves C, moving with constant velocity of negative I, negative j. We need to find an expression for S, which is the position vector of S. So if we go back to the diagram here, it's obvious that the point C here must be having position vector of 25i plus 25j, because O is the center of this square. So we can easily conclude that the position vector S is given by the initial position vector of 25i plus 25j plus the velocity of negative I, negative j times t. So we're looking at S being 25 minus t, and that's the I component, plus 25 minus t, which is the j component. In part C, we need to show that the vector SR is given by this expression here. Well, we know that the vector SR is given by the position vector of R minus the position vector of S. We have found that the position vector of R is negative 2 plus t, that's the I component, plus 1 plus 2t, that's the j component, and I will be deducting the position vector of S, which is 25 minus ti plus 25 minus tj. The only thing missing is for me to collect the I components together, the j components together, and simplify. So we're looking at minus 2 plus t minus 25 plus t, that's the I component, plus 1 plus 2t minus 25 plus t, which is the j component. This simplifies to 2t minus 27i plus the 3t minus 24j, all of these in meters as required. And finally, we need to find the time when the distance between R and S is a minimum. So I will start by finding the distance between R and S as a function of t. So I will be considering the magnitude of the vector we have found in part C. This is simply going to be 2t minus 27 squared plus 3t minus 24 squared and all square root. So I will expand this. I'm getting within the square root 4t squared minus 108t plus 729 plus 9t squared minus 144t plus 576. All of these under the square root. I will be collecting like terms together, which leads to 13t squared minus 252t plus 1305 square rooted. And we know that within the square root we're essentially looking at a quadratic. It's a smiley face quadratic, so I'm looking for the minimum and I will be exploiting the symmetry. So if we just look at this quadratic here, we can see that the coefficient of t squared A is 13, B is minus 252, and C is 1305. I will be exploiting the symmetry. The symmetry is always at x is minus b over 2a, which means that the minimum distance is when t is equal to minus the negative 252 over 2 times 13. This gives an answer of 126 over 13, which I can leave in exact form, or I can give to 3 significant figures as 9.69 seconds.